Hello again. From the last lecture, we got the form of conductivity, which is sigma. Let me just write in the beginning the heading recap of the form of conductivity. We got the form of conductivity, which is sigma, which is given by n p square tau by n. N is the density of electrons, E is the electronic charge, tau is the time scale between two successive collisions, and m is the mass of the electron. And uh, sorry, resistivity is inverse of that. Resistivity is inverse of that. This is annoying. So resistivity is 1 by sigma, which is given by m by n p square tau. So this is the form that we got for conductivity and resistivity from last class, and it was the conclusion from the Drude's basic assumptions. All right, he assumed that kinetic theory has a role to play in it. Like he translated the postulates of the basic postulates of the kinetic theory into the into explaining the conductivity or the resistivity of solid. So it was just in the framework of the kinetic theory of gases. All right, so this is the form that we got. Now we can derive or some estimates of length or velocity, as we can see, as we will see uh, as we proceed along in the lecture. So let's just say that you are doing an IV measurement. So you have a sample. All right, you have a sample. You send in current across it. This is the current direction, and you measure the voltage drop across the sample. All right. So from Ohm's law, V equals IR. All right, the linear relationship that we got, and R is rho into L over A, where rho is your resistivity of the material. L is your length of the conductor, and A is your cross-sectional area. So our sample like this. Sample like this. This is your A. This is your length of the. Okay. So now let's just take for example copper. Resistivity rho of copper is in the range of 1.7 into 10 raised to minus 6 centimeter, which is very low. And now we got the formula for resistivity, which is given by m by n p squared tau. Now we have to have an estimate of the density of electrons or the density of the charge carriers in copper. Now, or the so we can have an estimate of the charge carriers, estimate of the density of the charge carriers, and from that we can have an estimate of the mean time scale between two successive collisions, which is given by tau. We do have an estimate of resistivity. We know the mass of electron. We can have an estimate of the density of electrons or the charge carriers. We know the charge of the electron. We can have an estimate of tau. So this implies that tau is equals to m by n square root. All right. So now the density of copper. So the density of copper is given by mass per unit volume. All right. So let me denote it by D, the density, and we should not confuse it with by writing it with rho and all, because rho here is not denotes resistivity. So let's just stick with D. All right. So density is given by mass per unit volume. So let me just say, check if it's recording or not. Yeah, it's recording. Yeah, good. So now the mole, the number of moles of the material is given by number of moles of the material is given by the mass divided by the atomic mass. Alright, so this gives the number of moles of the material, the number of moles of the material it contains. Alright, so now if one writes E by A, which is mass, sorry, this is A who's confusing it. E by atomic mass, which is m by volume times the atomic mass, is given by, this denotes number of moles of the material per unit volume. Alright. So D by atomic mass, which is D is the density, will give you the number of moles of the material per unit volume. Alright. Now 1 mole contains 6.023 into 10 raised to 23 number of atoms. Alright. And this is the Avogadro number, Na number of atoms. Now for copper, with its outermost shell, which is 4s, it contributes only 1 electron. So the outermost valence shell, 4s subshell, it contributes only 1 electrons for each atom. So for each atom, let's say this is for each atom of copper, for each atom of copper, it provides 1 electron, 1 outermost electron from the valence shell. This is 4s for copper. So each atom contributes 1 electron. All right. So now density of electrons which is given by n, which is the number density of the charge carriers. This is we are calculating for the case of copper is equals to n is given by 6.023 into 10 raised to 23 into Z. This is given by Z. For each atom of copper, it provides one outermost electron from the valence shell, and this is denoted by Z. So this is Z in times the density of copper divided by the atomic mass. All right. So n is given by the number of electrons, the number of atoms it contains in 1 mole, times the number of electrons one atom provides, times the density of copper divided by the atomic mass of copper. So n given by Avogadro's number of atoms, Z here for our case is 1 times uh, you know, for let me just recollect. So density of copper divided by the atomic mass of copper. So 6.023 into 10 raised to 23 in 1 into this is T of copper is 8.96 gram per cc. All right, and atomic mass of copper is 63.546. So 8.96 divided by 63.546. This comes out to be 8.49 into 10 raised to 22 electrons per cc, which is 8.49 into 10 electrons per cc. This is the so n copper is your so this is the number density of the charge carriers for copper 8.49 into 10 raised to 22 electrons per cc. Now rho was given by m by n e squared tau, which implies tau is m by n e squared rho. Remember that this rho is the resistivity, which was given by rho equals for copper 1.7 into 10 raised to minus 6 ohm centimeter. You have to keep track of the your units. Be careful about that. So mass of electron is 9.11 into 10 raised to minus 31 kgs divided by 8.49. Sorry, write it extended way. So tau equals 9.11 into 10 raised to minus 31 kgs. Okay, divided by 8.49 10 raised to 22 electrons per cc, all right, into 1.6 into 10 raised to minus 19 coulomb times 1.7 into 10 raised to minus 6. So now, if you calculate that and keep track that CC you have to convert for SI units, you have to convert it into meter cube, and also this ohm centimeter you have to convert into ohm meter. So the final result is 2.4 into 10 raised to minus 40 second. If you recall from earlier lecture that we had an estimate of tau to be of the order of 10 raised to minus 40 to 10 raised to minus 15 seconds. So the mean time scale between two collisions for copper comes out to be of the order of 10 raised to minus 14 seconds, which we derived earlier. All right. Now, for this is for tau of aluminium. This is of the order of 8 into 10 raised to minus 15. All right, and these are all at room temperature. Fair enough. All right. So these are the room temperature values of the your mean time scale between two collisions for two different materials. Now you have in hand the time period, or the time period between two successive collisions. What you can calculate is the mean free path. Only if you know the mean velocity between two successive collisions. All right. Now, if sorry, let L be the mean free path of the electrons. Then L is given by V naught into tau, where V naught is the mean velocity of the electrons. Now, if you recall from earlier lectures where we recapped the kinetic theory of gases, we talked about the classical Maxwellian Boltzmann distribution. There we had a distribution where we took help from the equipartition theorem. It suggests that the mean kinetic energy of mv naught squared is given by half m v naught x squared plus v naught y squared plus v naught z squared. All right. Now from equipartition theorem, each degree of freedom will contribute half kBt. We know that in time half mv naught squared is equals to half kBt plus half kBt plus half kBt. This is easy. This is equals to 3 by 2 kBt. This is the Boltzmann's constant. So V naught is given by root under 3 kBt by m. This implies that V naught is proportional to root under m. Root under t, sorry, pardon me, root under t. So the mean velocity of the charge carriers of the electrons depends on the square root of t. All right. So if we calculate this, this is 3 into 1.38 into 10 raised to minus 23. We calculate at room temperature, this is 300 Kelvin, and this is your M, which is given by 9.11 into 10 raised to minus 31. This comes of the order of 10 raised to 5 meter per second. All right, this is what we get from using the equipartition theorem and the classical Maxwellian-Boltzmann distribution. So from here, we can have an estimate of the uh, mean free path of the charge carriers of the electrons, which is given by V naught tau is equals to of the order of 10 raised to 5 into 10 raised to minus 14 to 10 raised to minus 15. This is in meter per seconds, and this is in second. So this is given, by 10 raised to minus 10 to 10 raised to minus 9 meter, which is given by so this is equal to 1 angstrom to 10 angstrom. So the typical mean free path that we get, the estimate that we get of the typical mean free path of the electrons or the charge carriers is around 1 angstrom to 10 angstrom. Now, if you connect, so this is the typical length scale of the lattice of the distance between two lattice sides, right? The lattice size consists of uh, the positive ions, the immobile positive ions. So if this be the length scale, if this be the mean free path of the electrons, then so so these are your typical immobile ion cores. If the electrons are randomly moving about, so they move in between the lattice sides. So this is your electron E minus. So this gets to this point, this gets to this point, this can get to this point. So this is the typical length scale or the mean free path of the charge carriers. So Drude naturally that Drude assumed that the electrons undergo collision with the positive ion cores. Fair enough. So it was natural at that point to assume that as because the typical length scale, the mean free path of the charge carriers of the electrons, it comes out to be 1 angstrom, 10 angstrom, which is also the typical length scale between two positive ion cores, the distance between two ion cores, the lattice sides. It was natural to assume that the electrons are undergoing collisions with the positive ion cores. So that was Drude's assumption. So now we have an estimate of the charge density of the charge carriers. We now have an estimate of the typical length scale or the mean free path of the electrons from the, and we derived it from the Maxwellian-Boltzmann mean velocity distribution. And we took recourse to equipartition theorem to have that estimate. All right. So although this was a fantastic model, it even today some approximations are done with this in the realistic case. So it was a very simplistic model. It came from the kinetic theory. It was built under the framework of the kinetic theory, but it has some limitations and the flaws were quite evident when some experiments or some experiments showed that the Drude theory has some limitations. So, what are the limitations of Drude's theory? Limitations of Drude's. All right. So, if you go back you commented that V naught from the equipartition theorem was proportional to T. You commented just a few minutes back. So this was with the consideration that the electrons are classical particles. But in reality, this is not the case. You know that electrons are quantum particles. They are fermions, and they obey the Fermi Dirac statistics rather than the Maxwell Boltzmann distribution. Alright. So in reality, electrons are quantum particles. They are not classical particles, as Drude assumed from the I mean, in the kinetic theory of gases, it was assumed that the electrons are classical particles like billiard balls. They are undergo collisions with each other and also with the walls of the container. But they are fermions. They are quantum particles and they obey the Fermi-Dirac statistics. So as we go along in the course, as we go deep down in the course, we'll derive that, and we will see that this velocity in actuality is independent of temperature. All right. So V naught does not depend on T. Rather, with considerations that the electrons are quantum particles and they obey the Fermi-Dirac statistics, we find that V naught is typically of the order of 10 raised to 6 meter per second, which is 10 times larger than classical considerations. All right. So now we know that electrons are quantum particles, and we will estimate deep down when we go deep down in the course. We will see that V naught is typically of the order of 10 raised to 6, which is 10 times larger than what we estimated from classical considerations. Also, found out that rho is equals to m by n e squared tau. So we know that as we go down with temperature, rho decreases, resistivity decreases, we know. All right. So as we know that as we go down with temperature, resistivity decreases, right? For copper also, which is a metal, the resistivity decreases. Now as resistivity decreases, uh, so you have to have an increasing tau, all right, because tau is in the formula for resistivity. So as T goes down implies rho goes down, which implies t goes up, tau goes up, sorry, tau goes up, the time scale between two collisions goes up. So from 10 raised to minus 15 to 10 raised to minus 14, it has escalated to 10 raised to minus 30 seconds. All right. Now, this changes the mean free path of the electrons. So L, which is V naught times tau, V naught has become 10 raised to 6 and tau has become 10 raised to minus 30. So this of the order of 1000 angstroms, which is speed, sorry, E 1000 or 1000 to 1000 angstrom. All right. So it's a drastic change in the mean free path of the electrons. So, but this is not equal to the lattice spacing of the material, which is typically of the order of 1 to 10 angstroms. But this is not the case for when we consider that electrons are quantum particles. So it is at least twice or 3 orders of magnitude larger. So this was the failure of Drude's theory. All right. So it was not clear from where exactly is this scattering coming. Drude naturally assumed that as because the lattice spacing is matching, is of the order of the typical mean free path of the electrons. So the electrons should undergo collisions with the lattice, the positive ion cores. But this is now not the case. So it was a bit confusing from where the scattering is coming, so that the typical length scale or the typical mean free path of the electrons comes out to be of the order of 100 to 1000 angstroms. Even people have reported like tens of centimeters in typical materials, the mean free path. This is quite high. So it's not clear from Drude's theory how the scattering mechanism is coming. There, the Drude's theory falls. These are the all the drawbacks of Drude's theory. It was not able to estimate the actual reason behind the typical scattering mechanism. So in this lecture, we learned about typical estimates of the mean free path from Drude's assumption and typical time scale between two successive collisions for different materials. We estimated that, and we learned about some drawbacks of Drude's theory. Although it was a very ingenious theory, it's still today celebrated, but some many approximations are done with this theory, but it falls at certain places. So for today's lecture, we end here and we go back when we go proceed further to Hall effect and other interesting properties of materials from we derive that. Thank you, everyone.